Welcome to this lecture. Today we'll discuss another method for the analysis of trusses, namely the method of sections. This method is based on the solution of a non-concurrent system of forces. We already looked at the following methods that can be used to analyse simple trusses, including the qualitative method. This allows us to assess forces in truss members qualitatively, allowing us to understand whether members are in compression or tension. Method of joints. As we've already seen, this method employs linear equilibrium, and it represents the truss through several systems of concurrent forces. The method of sections, which we'll be looking at today. This method employs both linear and rotational equilibrium. It represents the truss through a system of non-concurrent forces. And the graphical method. This method describes the state of forces in a truss graphically using vector addition. In this lecture, as I said, we'll be discussing the method of sections. The solution of a truss using the method of sections begins with finding reaction forces by generating a free body diagram. The truss is disconnected from supports and reaction forces are applied. The reaction forces are found from three equilibrium equations, including the sums of forces in the horizontal and vertical directions and the sum of moments. Given that the reaction forces are found from equilibrium equations, this truss, disconnected from the supports, is in equilibrium. That means that every part of this truss is in equilibrium. Now we use our imagination to cut the truss into two parts. We make a straight imaginary cut and separate the parts of the truss. It is important to remember that only three non-zero force members can be cut. Otherwise, it will not be possible to solve the truss, as we only have three equations of equilibrium in 2D. If you need a reminder on zero force members, you can find this in the previous lecture on the method of joints. Since the whole truss is in equilibrium, its parts should also be in equilibrium. As you can see, the parts of this truss are not currently in equilibrium. Therefore, we should add internal forces in the directions of the cut members on both parts of the truss. Note that these internal forces represent the influence of one part of the truss on the other. Each part of the truss should be considered as a rigid, non-deformable body. Now we have two rigid bodies with forces applied. Both bodies should be in equilibrium. Because the corresponding forces acting on both parts of the truss are equal, only one part of the truss needs to be solved. In selecting a suitable part of the truss, we will be guided by two principles. First, the selected part should have the fewest forces applied. Or second, the selected part should have the most convenient geometry. Based on these two principles, the right part of this truss is the most suitable and easier to deal with than the left part. And the left part of the truss can now be discarded. Let's consider the problem at hand. We now have a rigid body with forces applied. The system of forces is non-concurrent. Therefore, to find the unknown forces, we will use three equations of equilibrium. We can write only three independent equilibrium equations for a planar problem. A standard set of these equations includes the sum of forces in the horizontal direction, the sum of forces in the vertical direction, and the sum of moments. Since there are only three equilibrium equations, only three unknown forces can be found, and therefore only three non-zero force members can be cut. In writing equilibrium equations, the best practice is to try and achieve only one unknown force per equilibrium equation. This can be achieved by using different possible sets of equilibrium equations. The standard set of these equations includes two sums of forces and one sum of moments. However, other sets are possible. They can include one sum of forces in the horizontal or vertical direction and two sums of moments about two different points. Another possible set is three sums of moments about three different points. In selecting equilibrium equations, it should be remembered that only three independent equilibrium equations can be selected, regardless whether it is translational or rotational equilibrium. The fourth equation is a combination of the first three and can only be used for validating the solution for the forces. Let's consider how to achieve only one unknown force per equilibrium equation. This can be achieved by using a certain set of equilibrium equations in a certain order. For example, in the part of the truss considered earlier, we can start with the sum of forces in the vertical direction. The solution of this equation gives the value of the vertical component of force F24, from which the force F24 can be found. The second equation is the sum of moments around joint 2. Since the lines of action in forces F21 and F24 intersect at this joint, these forces pull this joint rather than rotate around it, and as a result only force F34 enters this equation, and therefore we can see that its value is equal to 0. The third equation is the sum of forces in the horizontal direction, the solution of which gives force F21. The other possible set of equilibrium equations that can be selected contains the sum of forces in the vertical direction and two sums of moments about joint 2 and joint 4. In this set of equations, only the third one is different from the equations in the previous set. The third equation is the sum of moments around joint 4. As you can see, the lines of the action forces F34 and F24 intersect at joint 4 and therefore do not rotate around it. Only the forces F21 and the reaction force VR enter this equilibrium equation. The solution of this equation results in the value of force F21. The third set of possible equilibrium equations consists of three sums of moments. Here, the new equation is the sum of moments around joint 1, which gives the value of the vertical component of forces F24. In writing the equation for the sum of moments around joint 1, it is necessary to find the contribution of force F24 to the moment. The imaginary cut can be made at an arbitrary place and does not have to be a straight line. We assume that it is curved in the way shown in the right top corner and cuts member 24 at joint 2. In this case, force F24 and its components are applied at joint 2. The line of action of the horizontal component intersects joint 1 and only the vertical component rotates around this joint. The other way of looking at this is to consider that the right part of the truss is a rigid body. Force F4 is an external force for this body. Given that we are interested only in external behaviour of the right part of the truss, we can move force F24 along its line of action to joint 2 without altering its effect. The analysis procedure for the method of sections can be summarised as follows. First, the reaction force should be determined. Second, the truss is cut into two parts, considering that only 3 non-zero force members can be cut. The easiest part to solve is selected, and the internal forces in the members cut are applied. An appropriate set of equilibrium equations is selected. The equilibrium equations should be selected using the following guidelines. Each equilibrium equation should have only one unknown. The sums of forces do not necessarily give the easiest equilibrium equations, and points of intersections of lines of action of unknown forces should be selected for writing sums of moments. Want to put this into practice? Let's solve some trusses using the method of sections together.